Good morning, everyone, and welcome you all for today's guest lecture. Today we have Dr. Sourav Bhattacharjee uh, with us to talk about modeling tissue fabric based on autofluorescence from concept to application. Let me take a minute to give us a brief introduction about our speaker today. So Dr. Sourav joined the Medical College and Hospital Kolkata in 1997 and graduated with an MBBS in 2004. After a brief period of residence training in orthopedic surgery, he joined the master's degree in molecular sciences, cell biology at the Vrije University, Amsterdam. In the meantime, he moved to Edinburgh, where he worked for almost 14 months under the supervision of Professor Vicky Stone at Napier University. Upon finishing his master's degree, he began his PhD at the Wageningen University, Netherlands, in 2008. He successfully defended in 2012 with a very good thesis grade and several research papers. Following that, he worked for about a year as a postdoc at the University of Twente. In March 2014, he joined Professor David Braden's group at UCD as a postdoc working on the EU FP7 funded TransInt consortium trying to develop nanoparticles drug delivery platform for oral insulin delivery. From February 2016, he joined the UCD School of Veterinary Medicine as an assistant professor in veterinary anatomy, while also trying to develop his niche of research encompassing a broad range of nanobiotechnology and develop advanced microscopic tools for effective diagnostics and drug delivery platforms. So today he's going to talk about modeling tissue fabric based on autofluorescence from concepts to applications. And over to you.
Okay. Well, I'll stand here. That probably is good. First of all, a very good morning from Tartu. Estonia has been a country which has been immensely gifting to me. I have been coming here over and over again, and every time this country gives me even reasons to be more gratitudeful. So thanks a lot. Thanks a lot for inviting me, and thanks again, a very good morning for the people who are attending this lecture here and the ones who are also joining over Zoom. So thanks everyone for coming over, especially if you're from UK or Ireland. It's pretty much 8 o'clock in the morning. So thanks for your perseverance and love for science. So just to give a quick introduction, actually, I come from this Emerald Island, which is sometimes called Ireland. And you can pretty much see it's pretty lush green with lots of clouds and lots of rain, which sometimes we are not very happy about, but we deal with it in our own way. And I'm an assistant professor in the School of Veterinary Medicine, where I do a lot of research, especially on biophotonic studies. But at the same time, I'm also engaging with anatomy teaching and learning quite a bit as well. Now, there are a couple of things I will first draw your attention towards is the title of my lecture, which is Modeling Tissue Fabric Based on Autofluorescence from Concepts to Applications. So let me make it very clear. This talk is about autofluorescence, about tissues. And I'll come into upcoming slides into more detail about this. And the next important bit is from concepts to applications. And I want to make it absolutely clear at the very beginning of this talk that the application that I'll be focusing very much here will be on the cancerous tissues, because there are a lot of applications for biophotonics platforms, especially with the advancements that we have been achieved in the last decade or so, where there can be incredible kind of a leap forward in the way biochemically or imagically what we can find in cancerous tissues. And that will become a very important bit of my talk here today. And autofluorescence is also very, very important. Now, in modern biomedical research, I think most of you, if not all of you, are already quite accustomed with fluorescence-based microscopical studies. We do a lot of immunostaining and different other studies. But what I am trying to convince you is that even without staining, some of the tissues, in fact, a lot of tissues that we don't care often, or sometimes we are a bit ignorant about, they are just autofluorescent. They fluoresce themselves. So rather than spending a lot of time, lot of resources for staining those tissues, unless there is a particular reason or a driving reason, we can just focus on the autofluorescence that is already quite informative and can give us a lot of information on these tissue beds. Now let's focus on the very fundamental stuff first. Why do tissues autofluoresce? And in fact, I would like to reverse this question and throw it a question towards you. Why should not it autofluoresce? If you look into the components of tissue, any tissue as such per se, there are plenty of materials inside it which is fluorescent, and we know that. For example, today we will be focusing a lot on the tumor tissues that's filled with basic material, extracellular matrix, packed with collagen, fibrinogen, name it, all these fibrillar proteins, and of course blood. There are a lot of materials that are already fluorescent. There's an exhaustive list of that in pretty much quite some publications. And if you go through them, you will find that tissues are autofluorescent inherently, even without any staining. Now, I'll go into detail in the upcoming slides. But very much from the strands over here, I'd like to take you to the tapestry of cancerous tissues, because cancer tissues are kind of particular type of tissue which is aberrant, which is growing super fast, and which is kind of providing a great matrix, which is messy, which is pretty heterogeneous, and that is causing a lot of biochemical changes within itself that can be seen by microscopical tools. And one of the key factors of any tumor tissue, like one of the cartoons that I am showing here right now in the screen, that it's pretty heterogeneous. And there is a lot of deposition of different materials, which again are autofluorescent. Now let's quickly have a look on the tumor microenvironment. And this is particularly interesting. And I would say that even from the Roman times, they actually found out that tumor itself is a very particular type of entity, and it has its own pathobiology and microenvironment. Now just look at what I'm showing over here. This is kind of a scheme showing a solid tumor, which is growing very fast, and its cells are dividing completely uncontrollably. Now look at this tissue mass. It is growing. You should already appreciate the different fibrillar proteins that are being accumulated over here. The cells are growing super fast. They're dividing and continuously dividing. It's like a train which is where the brakes have failed. It continuously keeps dividing with more and more mitosis. And that brings us to its fundamental pathobiological requirement in its microenvironment. If so many cells are dividing so fast, it needs a steady and probably overload of nutrition. And that nutritional supply comes from the blood. So tissues or solid tumor tissues, they're extremely evil and extremely manipulative in a way that they dupe our body's immune system, and they try to create new kind of angiogenesis where they are developing new kind of blood vessels. And when I say new, I particularly mean it's a new kind, and it's often defective because these blood vessels are being developed in a super high speed. So the angiogenesis is happening, I mean, it's very fast without control. So although these blood vessels are able to supply that extra need of blood inside tissue, they are also aberrant because things are done pretty fast. These blood vessels, this angiogenesis is happening hastily. So what happens is a lot of these blood vessels, although they are carrying blood and providing as much as nutrition they can, a lot of these blood vessels, they have defective walls. That means these walls are typically known for having fenestrations, and through these fenestrations, the blood from intravascular component that actually seeps out to that tumor matrix and accumulates there. So if you have a solid tissue and if you cut it over as a slice, you will see there are black conglomerates over there, which are nothing but digested blood being accumulating inside the tumor tissue. Yeah. Okay. Yep. This one? This one?
This one.
Yeah. Yep. No, it's not moving. Sorry, laser. This might move, yeah. Okay. So this is the kind of a tumor matrix that we were talking about, where the blood vessels are coming over, they are defective, and there are fenestrations within the blood vessels through which the blood is coming out and accumulating within the tumor matrix. While we will go through the further data slides, I would like to remind some of these particular properties of a solid tumor, and we will try to find them in microscopical imagery that I'm going to demonstrate in next few minutes. Another important thing that goes on, particularly from a biochemical perspective, inside the tumor is that because of this high demand of nutrition, of course, oxygen as well, which the blood supply keeps providing, this defective or aberrant angiogenesis, still after some point of growth, this tumor tissue or the oxygen demand supersedes how much the supply this aberrant angiogenesis can deliver. As a result, there is not often enough oxygen for the tumor tissue cells to have aerobic respiration. And thus, anaerobic respiration begins. This anaerobic respiration produces a lot of acidic materials that are deposited inside this tumor matrix. So if you have a solid tumor slice, and you can check it with a litmus paper sometimes, that the tumor tissue, inside tumor tissue, is often very acidic due to deposition of these acidic materials, which are simply byproducts of the anaerobic respiration of this rapidly developing and dividing tumor cells. So this acidity, due to low oxygen tension inside tumor, will also become an integral part of our discussion in the coming slides. Now, the point I'm trying to make here is, of course, there has been great leaps has been made to understand the tumor microenvironment and its pathobiology. And we have made a lot of advancements in the last couple of decades, especially. And over the biophotonics tools has been revolutionized with newer advancements and feedbacks and plugins. Now, I am particularly interested in autofluorescence and per se on fluorescence microscopy. The major reason is that the power of fluorescence microscopy is it's fast, it's reproducible, and very important, these are ultra-sensitive platforms. And this ultra-sensitivity means a lot for us. Because if you remember, one of the key messages in oncotherapeutics is that early detection is the key. So when we have an ultra-sensitive platform that can even detect even minuscule changes within the tumor matrix, that should enable us spotting something is going on or a defective pathobiology within the tumor matrix at a pretty early stage. And that should definitely help us detecting or having at least have a kind of a screening platform to have tissue samples and then find out which are where or which are the tissues where something suspicious or dubious is going on. And then hopefully we can, even with the advancements of current programming and the different algorithms available, who knows, in the near future, we will be able to automate this type of different emerging platforms where we will be able to discard, reject, or take out this entire factor of human error or empirical diagnosis. So that is where I'm very, very interested. Now, the type of microscopy that I'm particularly going to focus today, that we have done a lot of expertise and developed a lot of expertise in Dublin, is called fluorescence lifetime imaging microscopy, aka FLIM, F-L-I-M, fluorescence lifetime imaging microscopy. Now, before I show you the actual data, I would like to want to show you what do we mean by fluorescence lifetime. Now, because of the time crunch, I cannot go into a lot of the nitty-gritty of this discipline, but just let me give you a simple atomic model given by Bohr, or Bohr's atomic model. So simple, let us say we have a fluorophore, and so this is the nucleus, which has protons and neutrons. Neutrons are neutral, hence neutrons, and protons have a unique positive charge, but let's not focus over there. Let's focus on its periphery, where the electrons are revolving around, or they're moving around the nucleus in certain particular quantized energy states. I'm not going into, again, a lot of detail on the quantum mechanics or the quantum states of electrons, because that's not very pertinent from the perspective of this particular talk. However, let's focus on this electron. This is lower state, and the farther you go away from the nucleus, you keep on increasing to the higher energy states. Now, let's say we give or we excite this fluorophore, particularly this electron, with a particular laser wavelength, that means laser of particular energy, and we provide this energy gap. I have notified it here as delta E, which is nothing but the energy gap between the next higher energy state and the lower energy state. If we provide this energy with a light or laser of particular wavelength, we might be able to actually excite this electron so that this from ground state, it goes to the energized state, and it basically jumps over from lower ground state to the higher energy state over here. Now, once it reaches the higher energy state, then it again releases this gained energy, which has been provided to it by the laser, and then it falls down to the lower energy state. And this gap energy, delta E, that actually comes out as again, a kind of a photon particulate material. And I have given this equation over here. This delta E is equal to E2 minus E1. That is equal to h nu, where h is basically the Planck's constant and nu is the frequency. And that very emission is what we detect as fluorescence, and we have used extensively over the last couple of decades, especially in biomedical research. Now, this entire time for this electron to fly from the ground state to the higher energy state, which I'm showing here, and then again falling back to its ground state, this entire cycle of traveling by the electron, that is called fluorescence lifetime. And our modern gadgets have become so developed, and it has evolved so well, that nowadays we can very accurately measure this entire lifetime, fluorescence lifetime in real time, actually. In nanoseconds, in picoseconds, we are able to pick it up. And this lifetime is often given or denoted by this Greek letter tau. And from now on, I will be often using the term, this Greek alphabet tau, to denote fluorescence lifetime in this lecture, in this talk. Now, what happens is, why we are interested in fluorescence lifetime? Because fluorescence lifetime is of a fluorophore is very sensitive to the biochemical changes in its surrounding milieu. And when I say biochemical changes, I particularly focus on the pH of the fluorophore. So on an acidic environment, the lifetime will be different, and on a basic environment, the lifetime will be different as well. So when you kind of fluctuate, or the pH fluctuates within the milieu, the fluorophore's lifetime will also change. And that's very interesting, because without any further tissue manipulation, by simply using autofluorescence, we can try to figure out what is going on as far as acidity is concerned within a tumor matrix. We don't need to manipulate the tissue. We don't need to go for extra tissue processing. It's simply native tissue. We can just fix some slides and then measure the fluorescence lifetime. And by fluorescence lifetime, if we can find different segments of acidity within the same tissue matrix, and then we can present the data as in a kind of a color scale, which I will be showing you in next few slides already. The fundamental point is that, which I'm trying to make here, is that using fluorescence lifetime, aka tau, we are trying to develop a molecular pH meter. And that's very important. It has lots of different types of applications, but let's not go over there. Today, we will be focusing mostly on the cancerous tissue frames. Now, why are we interested in film? There are a lot of different conventional microscopic techniques, confocal microscopy, a lot of staining issues, protocols have already emerged. There are a few reasons why we are interested in it. The first one is, these are super sensitive, and I keep on repeating this term, super sensitive, ultra sensitive, because that should enable us a much earlier detection. And the more early the more we can prepone this threshold of detection, the more the success rate is going to be in the management of these cancer tissues. So these are much more, sensitive. They should enable us a much earlier detection. They can capture even the slightest changes in the tissue fabric. That is where we want to reach out. And it can it can, of course, early detection is the key to effective cancer management. Now, FLIM can demarcate different segments within a visibly homogeneous tissue. So a lot of tissues actually look homogeneous when you just look into their naked eyes, but there are a lot of things pathologically going on, maybe pretty much in a nascent state, but still going on somewhere subcutaneously. So it's not visible on the surface. But with the help of FLIM, we should be able to pick those or spot those aberrations out going on within a tumor tissue or within a tissue. And again, at a very nascent state. So that should enable us early detection. We can scan a wider viewing fields, which is, I think, over this, and I'll show you some data over today, where we have been able to scan sometimes even an entire tumor. So we have taken grids, we have stitched them, and the software has become so advanced now that the stitching basically looks seamless. And we can actually scan a big tissue slice, and we can slightly find where the things are going wrong if something is going wrong. This is robust, reproducible, and very important, immune to empirical variation. So you have data. So today when I show the data, it's in front of all of you. It's not empirical. It's not I am seeing it and I'm giving an opinion, or you are seeing it or you are giving an opinion. These are digital data which can be shared, shared over digitally over continents. You can have a conversation. So there's a lot of sharing possibilities here, which in fact takes out this empirical individualistic opinion / errors that might creep in. So that's a huge, huge advantage. Another thing that I'm very interested about FLIM, or probably not only FLIM, but inherently to many other fluorescence microscopy techniques, is that you can develop 3D slices or 3D visualization of the tissue. Whereas if you go by typical H&E, that is hematoxylin and eosin stained tissue, which still remains the cornerstone in histopathology, the most of the data is pretty much 2D. Whereas if you go by fluorescence, you can have a lot of 3D visualization. You can even cut through the slices. You can see what is going on inside. Now that's a huge kind of an advantage and a leap forward to where we stood even a couple of decades back. And very important, it is compatible with mathematical modeling of data and of course, automation. That's where probably we want to reach. We want to take out this entire factor of human error out of the equation and make it completely automated, which will be fast, which will be robust, and probably which will be more scientifically defensible, especially with the world that we are moving on. This is probably important. Now I will show some of the data that we have been able to gather. It's a study, it's an ongoing study. So a lot of things has been achieved, a lot of things are there still to achieve. So it's we are somewhere in the middle, but some of the things that we have found are already incredible. And I'm very much enthused to show you in this talk. So what we did is, and this is one of the perks of working in a veterinary school, that you get access to a lot of tissues, animal tissues, and animal tissues by per se, inherently probably, and these are stored tissues, these are preserved tissues in our hospitals, our pathology labs, and my colleague Ruth O'Connell has done unbelievable work and helped to give me this or donate me these tissues with, of course, ethical permission. So what we did is, we took some tissue samples and we got porcine small intestine samples. Now what happens is they were both normal and adenocarcinomatous, because we wanted to actually compare how the normal tissue looks, and then we wanted to put side by side how the cancerous tissue looks. So we have adenocarcinoma, so they're pretty much glandular. And then we also got some canine cancerous tissues. And just to give you the good news, we now also have normal tissues, canine normal tissues, which I will, when I rush back to Dublin, which will throw them, inside the microscope. So, but for today's talk, I will showing you only the cancerous tissues in case of dogs. So I have canines, gastric, small intestine, colon, and rectum, all adenocarcinomatous tissues. Other than that, although it's not mentioned here, I have also procured porcine large intestine tissues, normal tissues all, and we are looking for cancerous counterparts so that we can compare. What we did was, we have these tissues, we unstained, so we prepared slides. The slices were pretty much 4 micron thick. And because they are so thin, that is why we did not do 3D imaging. It was too thin. It's almost, we cannot take too many zeta stacks to develop very reliable kind of 3D visualization in 3D hyperspace. So all the data that I'm going to show you today, they're pretty much going to be 2D, but maybe tomorrow, when in my next talk, I'll have a lot of 3D samples for you. So stay tuned and join me tomorrow. What we did was we prepared this unstained tissue slide, so completely not stained. We have this tissue, we fixed it on a glass slide, and pretty much that's it. No H&E staining done, no cover slips. Simply the tissue on the slice. So then we did film investigation. It was done in Leica Stellaris 8 Falcon system, and that's an immensely advanced system. It can do wonders, and I believe you will see that. You will be convinced in next few slides. And the excitation wavelength was 440 nanometer, pretty much like that. Now we have a white light laser source, which is of course another great leap forward in our current laser technology. And the emission that we collected was 478 to 672 nanometer. So we pretty much took a long wavelength slice of the spectrum for the emission collection of the photons. The microscopy was done at room temperature because there was no need. These are fixed tissues, which we have already got. So there is no need for having it in 37 degrees centigrade or any higher temperature. Plus, there is another thing. We were measuring the tau, the fluorescence lifetime. And I have said it repeatedly that fluorescence lifetime is dependent on the localized environmental pH. What I did not tell you that this tau is also dependent on the localized temperature. And there are fantastic reports or literature available already, especially I read one which came out a couple of years back before COVID from a Japanese group. They are unbelievable work where they are actually prepared a molecule, a polymer actually, and they have created an intracellular thermometer. So this polymer, the lifetime changes based on localized temperature. And I can share with some of you, if you are interested, that paper. And that kind of changed their entire vision. It came out in Nature, some of the Nature paper, as far as I remember. Now what happens is they have created a polymer which gets inside the cells, and then it spreads throughout the cells. And by film imaging, they measured the different lifetime, and they actually proved that the nucleus has almost 1 degree centigrade or 1.5 degrees centigrade higher temperature than the cytoplasm around. What is even more exciting is they even compared the cancerous cells, and they saw that the general temperature, intracellular temperature, because of hypermetabolic states in cancer cells, they were even higher. So they created an intracellular thermometer. We here are working on an intracellular, I would say, molecular pH meter. We're not dealing with cells as such. We're dealing with tissues, of course. Now, so we did not want to vary the temperature too much. 25 degrees centigrade, that's where typical histopathology is done. And we are very happy with 25 degrees centigrade. We used a 40x microscope with numerical aperture 0.75. And then the data was acquired. We have this inbuilt LASEX software. So this is the version that we pretty much used. We measured the tau, that is the fluorescence lifetime. And we depicted the tissue samples, the viewing field, with a color scale. Now starts the actual show. I'm gonna trying to impress you with some of the glossy pictures. So these are porcine small intestine. We have normal tissue, we have cancerous tissue. First, I will show you the normal tissue, and then I will kind of spellbound you with the cancerous tissue because it's a pure evil, and you don't need any other markers. Just by seeing it, you know these are bad guys. So this is porcine small intestine, normal tissue. There is a color scale where we have mapped the entire fluorescence lifetime. And this is already incredible because if you look at the scale, this is 200 microns. So this entire picture came out of at least 128 square grids that were stitched together. So you can understand how big is the viewing field. And this is I'm pretty much impressed with the amount of viewing field that used to be one of the limiting factors in biophotonic studies in cells in case of tissues. I think we have pretty much addressed it. The stitching is seamless. It took more than 3 hours of acquisition, but here what we have got. So we have this entire tissue, and this is the fluorescence lifetime that has been pointed over in a color scale. So we started from 0.5 nanosecond to 6 nanoseconds. So anything that is on the bluish part is less in fluorescence lifetime, more pushing towards the reddish part, they have the higher lifetime. Fundamentally, what it means is, because we have created a molecular pH meter, we are basically using it as a pH meter, The more the color pushes or shifts towards the bluish and the purple side, it is more acidic. And the more the lifetime pushes towards the reddish part, it is going to be more basic / less acidic. So that's pretty interesting. Now let's look, apart from the pH meter aspect of it, I want to take you to this granularity, to this resolution of the image that you are seeing currently on your screen. I mean, the nitty-gritty, the detail, the granular structures that are emerging from it, from the tissue. This is porcine small intestine. We can see the individual villi. Now, I mean, there are multiple villi, and I will later show you an individual villus as well. You can see the different structures. It's pretty much detailed with high resolution, isn't it? And it's no wonder, because of all these figures, this presentation has become more than 115 megabytes. So that was kind of a stall. But anyhow, so this is the porcine small intestine normal. Let me show you one more porcine small intestine tissue. This is it. Again, lot of nitty-gritty. Now, we can see certain blue parts emerging over, and I told you blue parts are typically, it shows more towards, you are moving more towards acidity. And we have seen that for whatever reason, blood, especially when degraded blood, it is more and more acidic. There are multiple reasons for it. One of these was the hemoglobin, actually. The degraded hemoglobin is far more acidic, maybe because of digestion of its different porphyrin and pyrimidine bases, porphyrin base, different other materials inside it. Now, what happens over is we can see the different colors, we can see the different structures over it, and we can see the villi, which is spreading over it. We can see the overall, I mean, integument, the subcutaneous muscle tissue, subcutaneous muscles. So this is more towards the luminal side, and this is more towards the gut walls. Let me focus now on an individual villus. And I want to impress you with the resolution that we are receiving. Again, everything, the fluorescence lifetime mapped over 0.5 nanosecond to 6 nanoseconds. So that remains the same. 50 micrometer, that's the resolution scale over here. And that's inside one villus. And I want to take you through the different segments that we are seeing. We have an outer coating that gradually, I mean, this is pretty much of a green, I would say somewhere over this side. And then we have these internal detailed structures where we have a lot of blood supply. In fact, that's part of the lamina propria, that what you are seeing. And you can see the different structures pretty much stacked over here. And it looks pretty typical, normal, and nothing to be worried about. Now we go where it is to be worried about. So porcine small intestine, normal tissues. I've shown you 3 slides. Let me show you how the cancerous tissue looks like, and the texture is completely gone. This is porcine small intestine adenocarcinomatous. I think what you typically see is a complete failure, complete collapse of the typical histological structure that we are accustomed with normal small intestinal tissue. And we have lots of data, and my 2 students have done unbelievable work over this. So what you actually can see, a lot of fibrous tissue material deposition. Suddenly these yellow kind of filaments, they pop up. And I have a wonderful photograph in the next slide, of course, of these different materials. But what I want you to understand is that there is a lot of loss of tissue texture over here. And there is a deposition of material. There is quite a variance, and the heterogeneity is absolutely obvious. Now, we have seen a lot of these kind of fibrillar proteins. Can we focus on them? Answer is yes. So this type of resolution, of course, I'm pretty happy to see that some of you are already impressed with the resolutions that we are actually receiving. So these type of fibrillar proteins kind of knotting around, jotting around, they are coming over. And if we look even more carefully, you will see even within this proteinous or kind of fibrillar deposits, you see there are areas of red spots appearing. So there is a fluctuation of pH even within those materials. And that's something of a new kind of a perspective that we are emerging out of. Now, we can see that this tissue matrix, I think that's also pretty granular. And if we go back to our normal tissues, I think we can see pretty much what's the difference that's coming out over here. Another one, so this is again porcine small intestinal adenocarcinoma. You see all these depositions coming over. There are a lot of different variations. And what's very interesting is, if you look carefully, you will suddenly see there are patches emerging which are rather darker, which was not definitely visible in case of normal tissues. They were much more homogeneous. The autofluorescence was pretty much homogeneous. And what we found out was that this fluorescence lifetime tau of many of these places were close to, say, 3.8 to 4 nanoseconds. However, when we are getting into these parts, these are pretty dark, so there is less of a photon emerging from it. And we can explain it by giving this particular nature of cancerous tissues, which are pretty heterogeneous, actually. So there are places which are pretty dense, and there are places which are kind of thinning out. And I have more data in coming slides. It gives you kind of a glazed glass appearance. We can do some more mathematical analysis. Again, for the sake of time, I will not go into a lot of details into that. But here is this kind of a phasor plot, and this is the cancer tissue. This is the normal tissue. And so basically, this is a particular way of analyzing film data, which is inherent to Leica, actually. So they give this type of phasor plot analysis. And you can see for cancer tissues, this is the focus where most of the photons we have found. And there is spread of different other small variations. Particularly, we can call it some kind of a noise. And for normal tissue, it is much more different. Actually, geometrically, it is different. And the more you push towards the right side, the lifetimes are lesser. So it's kind of a more, it's kind of a, there is a subtle difference already we are visualizing. Now we are going through all the slices, and it depends how well, I mean, we need few more n numbers to actually start before going on to some statistical analysis. But the initial, difference is already pretty visible between cancer and normal tissues. We move on with canine adenocarcinomatous tissues, for example. This is canine gastric stomach adenocarcinoma. Again, it's a mess. It's heterogeneous, full of deposition of sometimes undefined materials, which we can understand probably different types of biomaterials, maybe proteins that are being deposited over here. More, again, strands of different yellow bits, patching, overlap, darking materials or spaces. It's a kind of completely different, very, very different in appearance than what we have noticed for in case of normal tissue. Now, this is small intestinal adenocarcinoma, and I told you that we have been able to scan an entire tumor. This is the example. This is an entire tumor. You can see the scale bar is pretty small because it's a big amount, and it took more than 5 hours, I think 256 grades, and we were able to catch up this and then stitch it up to make this kind of an imagery of this entire adenocarcinoma in canine small intestine. Pretty much, you will see these areas are pretty much like glazed, grounded glazed glass appearance, pretty much darker. Some areas are a bit more lighting up. You can see some blue areas, some areas that are becoming kind of more rugosed, trabecular, and that's pretty much of a carcinoma, adenocarcinomatous cancerous tissue developing over here. Move on, canine colon adenocarcinoma. Thicker muscles, so it provides way more granularity in adding colonic slides. Again, I think I don't need to convince you about the different fluctuations of pH, which is shown by different fluctuations of the color scale that we have provided over here. We see some blue patches. Some areas are a bit more dense. Some areas are becoming kind of more thinner. But we are pretty convinced that it certainly doesn't have that normalcy of a tissue that we are pretty much used to. This is again canine colon adenocarcinoma, a lot of fibrous materials that are being deposited. There are some reddish parts also appearing here. So there's a quite fluctuation of the pH that is going over here. And not only probably fluctuation of pH, the different molecules that are being produced, biomolecules produced by this evil called cancer, which is on a rampage. I would say that the tissues, the different molecules, their fluorescence lifetime also inherently change, because these are not always the molecules that we think they are. Sometimes they are just derivatives which are coming out of this very aberrant and abhorrent different pathways, signaling pathways that is going on over here. There are, again, you can see some bluish parts, most probably they are blood vessels or some blood that is being creeping out because of aberrant or angiogenesis. This is canine rectal adenocarcinoma. You will be able to see now the patches, dark patches, which are very, very visible. So the contrast is very much clear between the pretty much, I would say, lightened part and the darkened parts. The tissue texture is very, very heterogeneous. Now, rectal tissue can be a bit heterogeneous already, but cancer tissue is, I think, even more heterogeneous. And the cancer is pretty much spreading, I would say, because some areas are getting thinned or less autofluorescent. Some areas are pretty autofluorescent. And there is a fluctuation of pH. You can even see some minute details on these yellowish bits, which are somewhere here with a fluorescence lifetime, I would say somewhere around 2 to 2.5 nanoseconds. So there is a wide range of variation and fluctuation that we are also noticing in certain adenocarcinomatous tissues. Same here, the tissue texture is absolutely heterogeneous. There are some less fluorescent places. There are places which are pretty much lightened up. But I think we can already notice, even by the simple surface texture, that there's a lot of different parts or different segments within the tissue already that otherwise is always missing in a case of a normal tissue. Normal tissues certainly present you kind of a more of a trend, and whereas cancerous tissues, all these trends are gone. It's completely irregularly irregular. And whatever irregularity you have in a normal tissue, that's regularly irregular. So there is a kind of a difference, and that difference is visually already present to you. Now, I will quickly sum up the results in view of time, I think, but I should finish in time, actually. So FLIM imaging has captured images of tissue fabric with unprecedented resolution. And by the way, you can see these figures over here. These are the porcine large intestine tissue. I have not shown you because of the time crunch, A, and secondly, I don't have cancerous tissues as a counterpart to compare. But these are normal tissues, and I would like to quickly draw your attention to the unbelievable resolution that we are getting, actually. So really beautiful resolution. Now, we did all the acquisition under identical settings that made comparison possible from specimen to specimen. FLIM can already show, like in many of the previous slides, the different areas based on the pH particularly that are emerging within the tissue, and often as an ominous sign of something is wrong. Now, normal tissue demonstrated uniformity in texture and fluorescence lifetime across the viewing field, and that's pretty much gone in case of cancer tissues. Some alterations in tau or fluorescence lifetime was noted, maybe because of minor biochemical changes, but that's always to be expected. So in normal tissues, they were regularly irregular. In cancerous tissues, completely irregularly irregular. There are no patterns emerging. Cancerous tissue is grossly heterogeneous with major fluctuations of tau. I mean, that's the point I want to make. And cancerous tissue clearly demonstrated deposition of fibrous material that keeps it kind of that elasticity, especially in solid tumors. And the fibrous deposits had longer tau due to relatively higher basicity or less acidity, whatever way you want to put it. Now, what are our ongoing plans and work? Well, listen, the great news is we have got now acquired the normal canine tissue slices. Now we can compare with the adenocarcinomatous tissue slices, and that should be a great because we have porcine tissue slices, normal and adenocarcinomatous. Now we are having the canine tissue samples, carcinomatous already done, normal tissue here. So we have pretty much of kind of a comparison possible now. We need some further optimization of the microscopic platforms. Of course, we are learning more and more as we work more and probably make more mistakes. We plan to have a more granular understanding of the different tissue segments. I think we are still scratching pretty much on the surface. We have a lot deeper to go, and that will take time. We want to expand the scope of the study by including human tissue samples this year. So of course, we have done it in porcine, in pig tissues, in dog tissues. Of course, we would like to extrapolate it now to human tissues. We're trying to acquire. It's not always easy because of ethical constraints, and you often don't get enough N numbers, but we are trying to pretty much cope with it. Hopefully some success, touch wood, later this year. We are already doing data analysis with 2 sophomore students who I believe is already in the Zoom listening to this. And some of this data was already presented in last January, in the Microscopical Society of Ireland annual symposium, which was held in Limerick. So my 2 students, they presented the data, and of course, publish or perish, if I may say so. So we wish to publish these results in peer-reviewed journal later this year. Now, we have said all the glorified things. Now, what are the limitations? No study is out of faults or weaknesses. Well, first thing is the microscope is great. complex. It can do complex stuff, but complex stuff or enabling doing complex stuff also makes it very cumbersome to learn. So there's a lot to learn about it. There is a lot of expertise, and of course, it's pretty expensive, isn't it? Due to their second thing is tissue slices are not always compatible with microscopic platforms. Tissue slices are inherently granular. They're some inherently opaque. So it's not always easy to find or prepare tissue slices where light will actually pass through like a translucent material. So that takes some expertise, I would say, even more than some in some cases. We did not do any staining, so we just prepared the slides, but it still needs some tissue manipulation. And that is, of course, that means technically, whenever you are doing some tissue preparation or preparing slides, you are not actually looking into the actual native tissue, but you are having some kind of manipulation. In our case, the manipulation is way lesser because it's pretty much the native tissue that we have put on the tissue slices, but still there is some. And although we have not seen much of a variation in the tissue texture, we can match it. So that's pretty much of a good news. And not a lot of reference data is available in the literature. So we have data, but sometimes we cannot compare it to different other publications. So there is a scarcity of data, which is sometimes the issue. Now, quickly, the acknowledgements. Jennifer and Ellen, sophomore students in my UCD School of Veterinary Medicine, they have done an incredible amount of work. And Jennifer and Ellen, if you are listening to me, I'm proud of you, girls. So way to go. Professor Tore Sweeney, Dr. Marion Ryan, Ruth O'Connell provided with all the tissue samples. So thanks, Ruth, if you are listening. Max Gare, my partner in crime, and he has done all this incredible microscopy work. Of course, my two students have been integral part of the data acquisition team. And finally, UCD School of Veterinary Medicine and UCD OBRS scheme for providing me the little bit of funding that I actually needed for it. And finally, thanks to all of you for being patient. Thanks to the guys who have joined over Zoom. And what can I say? Well, let's have some discussion now. If you have any Q&As, thank you. Questions?
Yes, Ali Reza, you can go ahead.
Okay.
Hi, thank you very much, Sourav. It was very, very interesting. I don't know if you can hear me.
I can hear you.
Yeah. Sourav, the one thing that I didn't maybe got it when you started the presentation was about how do you make these specimens? Are they processed? I mean, you said that there is no cover slide or so. You mean that do you do any sectioning or without any sectioning, just the tissue, you put it on the slide and then make the pictures?
Well, first of all, we have not used any kind of staining. So what we have is that we have these tissue blocks, which we slice with microtomes. And what we don't do is we actually prepare the slides and we put the tissue slices on a glass slide, and pretty much that's it. We have not used many of the modification protocols or washing steps that we need to do hematoxylin eosin staining. So you can say our tissue slices were tissue slices until hematoxylin and eosin staining. So we did not do that, of course. So we did not put any other colors or any other stains. And whatever coloring that you are seeing, that is created by the software based on the different lifetime. So it's giving you a kind of an artificial color scale, giving on the life scale. So it's a pretty much of a genius of the software. We have not done anything. So we just took the tissue, made it 4-micron slices, put it on the slides, no cover slips because we wanted to get all the light. We did not want to put any cover slip, and straight away we went to the microscope, and that's what the colors you are seeing, those gorgeous colors are all by softwares. We have not done anything.
Yeah. And then how do you compensate for inter-slide variation in the intensity of the fluorescence? I imagine within one slide, in one region, you would have less intense fluorescence. In the other region, you would have more intense fluorescence. That is okay, that's fine. But if you have different specimens, different slides, how can you compensate that all of them are somehow looked at with the same kind of intensity or the same kind of fluorescence background and fluorescence that you can compare from one slide to another slide?
Well, the answer is, I think in one of the slides I already mentioned that the acquisition settings were always identical. So the data that you are seeing that is coming out of, I mean, basically it followed months of optimization, and finally that you are basically seeing the final outcomes. Now, there are a couple of interesting things. So first, the acquisition settings, so the numerical aperture, the resolution, different other settings, pore diameter, different things were kept identical, and we knew those values through optimization. So because they were identical settings, we could see or we could compare. That is number one. Number two, and this is very interesting for a lot of our audience probably, that one of the great stuff about fluorescence lifetime is that it is not impacted by photo bleaching. So fluorescence lifetime of a fluorophore hasn't got anything to do with photo bleaching. Photo bleaching happens, but still the fluorescence lifetime remains the same. And because we are acquiring the fluorescence lifetime, that is the data that I have shown it here. It is not that some parts are looking darker because of bleaching, because it has got nothing to do with bleaching. It has got that all to do with the fluorescence lifetime, which has not impacted by bleaching. And it's a major, major advantage which drives me or gets me attracted towards film. It is because of these two reasons that I think I can compare the different segments of the tissue. Now, finally, when I go back, we also want to do some other tests so that we want to be absolutely sure. And I can already explain, it's nothing secret. So we can have tissue slices, we can do hematoxylin staining and see those parts which are looking much more darker in film microscope and have hematoxylin data, and then we can probably overlap them, and that will be final confirmatory experiment. But as a microscopist, as a biophotonics guy, I'm already pretty much convinced because there is no bleaching. And even if there is bleaching, first of all, tissue autofluorescence is way less vulnerable to bleaching than many other standard fluorophores like Alexa, FITC, name it. So tissue autofluorescence is less vulnerable to bleaching. That's already an established fact. And second important thing is tau fluorescence lifetime hasn't got anything to do with bleaching. So if you see a darkened phase, and because our acquisition settings are always identical, that is how we can compensate. In fact, I don't think there is any compensation at all needed because we are not dealing with bleaching. Still, when I go back, I want to do some pilot experiments so that we can have tissue samples with hematoxylin staining and film, the same field, and we will overlap them. And that will be perhaps, that will give me enough reason to have one more Zoom call with you to show the data, if that answers it.
Yeah, thank you very much. Then no anti-fade or nothing is needed for avoiding bleaching, or so that is the message that I have seen the autofluorescence several times, but I never looked at it like this. Hence, you don't need any anti-fade or anything. It just stays stable.
So you don't need any anti-convolution or anti-bleaching algorithms because fluorescence lifetime is not affected. Two things. Another thing, Professor Fazeli, this is interesting, that fluorescence lifetime is not affected by bleaching. It is also not affected by the concentration of fluorophore. I think you already see the advantages coming over here. So it's purely fluorescence lifetime. That's what we have measured. I don't need to care about bleaching. I don't need to care unless I'm burning the tissue with some high intensity laser somewhere. I really don't care. And second thing is I really don't care about how much fluorophore, how many micromolar, macromolar. I don't care, I just go. And that solves a lot of problem, which you have already mentioned a few seconds back. So that's the good thing, guys.
Thank you very much. It was really, really interesting to see this
Thanks,
data.
Professor Fazeli.
Thank you.
Thank you. Thanks a lot.
Thank you.
Yes, please. Yeah.
My concern is like when it comes to clinical applications, so the false negatives could be more dangerous than the false positives.
Well, First of all, if you, let me just give you one example of the sensitivity. I mean, these molecules and our instruments, our softwares have become such sensitive now that we can literally go up to molecular sensing. So if even 1 or 2 molecules are playing some dodgy game somewhere, we should be able to see somewhere, provided we have enough intensity. Now, tissue is a kind of a difficult material for biophotonics because it's naturally opaque and everything. But then again, I mean, say something false, you're talking about specificity, so false negatives. This ultra-sensitivity of fluorescence is so inherently attached to a molecule. And I don't want to go into a lot of molecular details over here. I mean, when we are dealing with a tissue cancer microenvironment, I don't even know how many molecules we are dealing with because it's so complex. Now, getting false negative, because these emergence or this photonic emission is so precise and so particularly adherent to certain molecules only. It's kind of a molecular fingerprint. So it's much more precise and focused, where I should be very worried about hypersensitivity or having things wrongly perceived as positive, neither wrongly perceived as negative. That's what the biophotonics evolution is coming over. So I'm not much worried about that. I haven't seen anything like that. However, as I say, we will do some pilot experiments in coming future to actually have this hematoxylin eosin staining and put them side by side and overlap. That should be a confirmatory experiment as well. So if you ask me, I'm already convinced that it's pretty much of a molecular biomarker. If the molecule is not there, I will not have a false signal. That's pretty much it.
Thank you. And then probably the last question from me. So how's the ethical consideration background when you apply this film technique on clinical?
You mean ethical means acquiring the tissues?
Yes, yes. Like,
well, these tissues are, because, listen, I mean, our school is the apex of veterinary center. It's the only veterinary, so far, it's the only veterinary degree providing school in Ireland. And we have this reference pathological lab where we get all the tissue samples, biopsy tissue samples. So these tissue samples are, of course, you don't use the entire biopsy tissue samples. You use a little part, you do hematoxylin eosin staining, and you do the pathobiology. What it makes is, it makes a huge amount of chunk of tissue actually remaining and preserved in the cold storages forever. So fortunately, as I said, this is one of the parts of working in a veterinary school, especially if the veterinary school is that apex layer of the veterinary center or care in that country, that you have access to this wealth of tissues which are just preserved. So what you do is, if you go by that 3 hours of animal experiments, we are nothing but doing refinement. We are not procuring or harvesting new tissues. We are definitely not killing animals. These tissues were there, they will be stuck for quite a few years. So we are using the tissues which are already available. So I got a full ethical exemption. You go to Animal Research Ethics Committee, you say, guys, we are not doing anything new. It's not invasive. We're just having a slice of a tissue which is already there and probably no one is using it. And that comes with that, within that refinement hour of the 3 hours of animal research. So you don't actually need a full ethical kind of a clearance. Because of these things, you can go for an ethical exemption. And I pretty much got it within a week. So that's the ethical consideration. And for microscope, you just need money. No, I mean, it's just money, pay the money and then go. That's it.
thank you. Thank you very
Thank you.
much. Is there any more questions for Dr. Sourav? Okay.
No questions?
Yeah. So if there's no more questions, say thank you. And before we stop, we have a small.
Thanks to all. Thanks, Dolmini.
appreciation.
Thanks to everyone. And have a nice day.